So calculus uses this thing we call differentiation. And it's all about this thing we call differentiation. And differentiation is concerned with the rate of change. Now, what does that exactly mean? Well, the rate of change just measures how quickly something changes. And that's if it's in with respect to time, it's how quickly something changes. Otherwise, it can be due to other factors, but we'll go into that later. So, let's start with an example to make it a little bit clearer. So the speed is equal to distance over time. That's a formula that you should know for your GCSEs. So speed is equal to distance over time. So what this is saying is that speed is the rate of change of distance with respect to time. The reason this is in brackets is because it doesn't, in the syllabus, it doesn't say that you have to use with respect to time, but you do need to know what the something like speed is the rate of change of distance. And basically that means that speed is a measure of how fast or slow the distance changes over time. Obviously, if you have a higher speed, you'll be covering more distance over time. So the rate of change of distance will be the speed, but that's basically a measure of how quickly it changes. So it's with respect to time. One you might know, you might be familiar with, is the R rate. So that measures how quickly a virus spreads to other people, again, with respect to time. It measures how quickly it spreads. So it's with respect to time. So, when is it not with respect to time? Well, actually, differentiation is not strictly with respect to time. What we say is that differentiation, or dy over dx is how we put it, is the rate of change of y with respect to x. And that's why we put dy on top of this. This is why we put dy on top, because it's the rate of change of y, and we put dx on the bottom because it's with respect to x. Don't confuse this with a fraction. You can't times through by dx or anything. This is a function. We actually call it the gradient function or the derivative. So two names for it. So yeah, and it's a rate of change of y with respect to x, and we'll see why that's the case in a second. But first, let's just recap ourselves of what the gradient means. So here we have a straight line graph in the form y equals mx plus c, as I'm sure you're familiar with. So m here is the gradient. And the gradient is basically the steepness of the graph. So, for example, something like this will have a gradient of, let's say, 4, right? Or we'll say m equals 4. Here, this has the less of a gradient. It'll equal 2, let's say. Oh, in fact, that looks more like 1. Then we can get to 0, which is, it has no gradient. It's not steep, because a gradient is a measure of steepness. So the steeper it is, the higher the gradient. But because this has no steepness, gradient is 0. Here, we can say that the gradient is -1, because it's going downwards, not upwards. And here we can say it's equal to -4. So we see a decreasing gradient here, decreasing m, because the steepness is decreasing. So how do we find it on a straight line graph like this? Well, what we do is we get 2 points on the line, and then we find delta y, which is delta is just a Greek letter, which means the change in, and delta x. So, and we say the gradient is delta y over delta x, or the change in y over change in x. Now you can already see kind of a familiarity between dy over dx, the rate of change of y with respect to x, and this here. It's the rate of change of y with respect to x. But the gradient just measures it at 1 point, which I'll get into that later. So yeah, let's so another way of writing that is y2 minus y1 over x2 minus x1, where this is this is x2 y2 x1 y1, like so. So that is how you find the gradient of a line. You just get 2 coordinates on the line and you find the change in y over the change in x. In fact, let's do an example. So let's say this, in fact I'll do the example in blue. So we'll say this is 4, 6, in fact, it looks more like 6, 4. And let's say this is 3, 1. Then what we do is we just substitute it into this formula here, which will give us 4 minus 1 over 6 minus 3. That will give us 3 over 3, which is 1. So our gradient is 1. So what is dy dx then? Well, dy over dx is basically measures the gradient at every point on the line. So it would also be equal to 1 in this case. But that's because the gradient is constant. And I'll come back to this later. Now, this is where dy over dx really shines, I guess. Because if you think about a curve like this, if I wanted to find the gradient at point P, I'd have to draw a tangent, which is a line that just touches point P. And then that would give me the gradient at point P. All I'd have to do is, again, find the change in y over the change in x. Like so. I'd find the gradient at that point. But the issue with this is, unlike the straight line graph, the gradient is changing, the steepness is changing throughout the whole graph. So the gradient function, or the derivative, dy over dx, can be used to find the gradient throughout the whole graph. So we can pick any point and we can find the gradient without having to draw a tangent every time. Do bear in mind that drawing tangents is part of the GCSE specification. So this method might still have to be used because you can only find the gradient function if you have the formula. You can't just find it from the graph. Okay. Now let's actually do an example where we work out the gradient. And we need to use these 2 rules here. They might look a bit complicated, but basically what it means is if you have y equals kx to the n, where k and n are numbers, then dy over dx is equal to knx to the n minus 1. This might look complicated, but all you're doing is you're moving the n forward and you're subtracting 1. So you're moving the n here, and you're subtracting 1 off the n. We also have this case, if y equals k, where k is just a number, then dy over dx is 0. So let's use it on this example here. This is the same graph as we had before. So now, if we want to find dy over dx, what we do is we bring this 3, which is our n, we bring it, in fact, let me get rid of these. Yeah, we bring the n to the front. So our k is 1, so we just get 3 at the front, and then we take 1 away from the power. Okay, so the second bit, now k is 2. So remember, when we bring the n to the front, we also have to multiply it by this 2. So we get minus 4. And then again, we take 1 away. We could put 1 here, but x to the power of 1 is x. So it doesn't really matter. Now, here, remember, this doesn't have an x. It's just a number. It's a constant. So we can use this to get plus 0. But we don't have to write plus 0. The constant term just disappears. So this is your gradient function. So the reason, I just quickly want to, you don't need to know this, but the reason that this constant term just disappears is because if you think about it, you know from your indices rules that x to the 0 is 1, because anything to the power of 0 is 1. So if you think about it, this is x to the 0, because 6 times 1 is just 6. So when we move the 0 to the front, we times by 0, like that. And obviously when you multiply by 0, it disappears. So that's how that works. Yeah, but that's fine. Okay, so if we drew this here, we would get something like this. Something like that, right? So this is plotting dy over dx. And this is why it's called the gradient function, because it denotes the gradient of this curve. You can see the gradient is very high before it hits 0, right? And then it goes negative for a bit, like it does here. So the gradient goes negative, and then it hits 0 again, and it goes positive again, right? So that's kind of like how it works. And obviously, just going back, the reason that this is 1 all the way through is because the gradient never changes. So yeah, it's basically just plots the gradient of the graph as it changes. So now we could put in any value of x and we get the gradient at that point. So for example, we could put in x is 2, and that's, well, 2 squared is 4, times 3 is 12, and that's 8. So we get 4. So we know that 2 must be around here, because that's when the gradient is increasing. Another point we could put in is 0. Let's try 0. Or let's try 1. Well, that's going to be 3 minus 4, which is minus 1. And we can see that the gradient is negative at that point. Let's try x equals 0. So this is x equals 2. This is x equals 1. Let's try x equals 0. So we get x 0 squared minus 4 to 0, which is just 0. So, I haven't drawn this graph super accurately. But yeah, basically at 0, this will have 0 gradient. If we go back, you can see that when we have a 0 gradient, it's just a horizontal line. We can see that here it is a horizontal line. And we'll go more into that next video. Let's try another example. Let's try y equals 4 over x. Now, when I showed you all that graphical stuff so you can understand the theory behind it, you will usually just be given a function like this and asked to differentiate it. Differentiating something is basically putting it in the derivative form. But before we do that, this one's a little bit more messy because we don't have it in a nice form like this. Let's try and find that form. So we can rewrite this as y equals 4 times 1 over x plus 2 times 1 over x cubed, like that. All I've done is I've taken the 4 and the 2 outside of the fraction. And now this kind of looks familiar. We can convert this into minus 1, the power of minus 1, because remember 1 over is the same as minus 1, and we can do the same here. We can just make the power, we can make it negative. Okay, so now that we've got it in that form, we can just do the same thing. We bring the power over, so we get minus 4, and we subtract 1, so we get minus 2 as our power. Over here, we get minus 3 times 2, so we'll get minus 6x. Take 1 from that to the minus 4. Sorry, this would be dy over dx, because we're differentiating. Okay, so hopefully that makes a little bit more sense. If you want, we can put it back into fractional form by doing the opposite. So we get minus 4, and then we change it to 1 over x squared minus 6, and then we get 1 over x to the 4. And then obviously we can multiply these fractions out, giving us minus 4 over x squared minus 6 over x to the 4. But if it doesn't ask for it in that form, this will be just fine. Right. Let's do one more example. So it says find the gradient of the curve y equals x minus 1 over x at the point 2, 3 over 2. And this goes back to if we had the graph in front of us, we could just draw a tangent at x equals 2 and that would give us a gradient. But we don't have the graph, but we do have the equation, so what we can do is, again, we can convert this 1 over x into x to the power of minus 1. And then we can differentiate. But look, this has a power of 1. So we bring 1 to the front, but 1 minus 0 is x to the 0. So remember, x to the 0 is just always equal to 1. And this goes into that, like we learned here. But because this is x to the 0, we can actually convert this to 1. And I've just swapped them around. So that's the derivative. And we can change that to 1 plus 1 over x squared if we wanted to. So another rule for this would be, in fact, I'll add it to this. You don't need to remember this so long as if you remember that, but if y equals kx, then dy over dx equals k. So we've gotten rid of the, so we just get rid of the x. So 1x becomes 1. Yeah, so that's what we get. But remember, it asks to find the gradient of the curve at 2. So, but now, because this gives the gradient of the graph for any value of x you put in, we can just put in 2 into this instead of x, and we get 1 plus a quarter, which is 5 over 4. So that's our gradient.